Welcome to the video for problem 231 of Engineering 623. And this is an interesting problem and a straightforward one. We want to construct a bounce diagram in this problem. Specifically, what the problem says is the following. It says, plot the bounce diagram for the transient circuit shown in the accompanying figure. Include at least 3 reflections. What is the total voltage at the midpoint of the line? In other words, at Z equals L over 2, at time T equals 3L over VP. So the first thing we can do is to calculate the reflection coefficients at the load and at the generator. And this is very easy. At the load, we have the load impedance 100 minus the characteristic impedance 50 divided by the load impedance plus the characteristic impedance. So we get gamma L equals 1/3. On the other hand, at the generator impedance is 25, and again, the characteristic impedance is 50. So when we use those values, we get 25 minus 50 over 25 plus 50, and this time that comes to minus 1/3. And then we need to figure out the initial positive voltage wave traveling on the transmission line, and we can do that with a voltage divider. Since the characteristic impedance of the line is 50 and the generator impedance is 25, then the voltage divider equation will give us V plus is equal to 50 divided by 50 plus 25 times the generator voltage, which is 10, and so this is 20/3. And that's really just about all we need for this problem. They tell us to construct a bounce diagram for 3 reflections. So our bounce diagram, and for any of our problems that we're likely to do in this course, then the bounce diagram will look like this. If we request for 3 reflections, here's your initial wave, and here's the first reflection. That's a reflection off the load. And then a second reflection would be a reflection off the generator. And then finally, we have a second reflection off of the load. And these lines look exactly the same. The endpoint here, the maximum value of Z that we need to consider is L. And we see that this first line, the first wave, gets to Z equals L at time T equals L over VP, and the reflection then starts traveling back to the generator, and it gets there at time 2L over VP, and then a reflection of that reflection will start traveling back to the load, and we'll get there at 3L over VP, and then the final reflection will get back to the generator at 4L over VP. And of course, we could extend this and take into account more bounces if you wish, but we were not required to do that in this problem. So you could go ahead and you know, like say, if you were faced with a problem where you were told to construct a bounce diagram with 3 reflections, the diagram will look exactly like this. The only difference would be what are the magnitudes of these voltages. And so now we're in position to do this. So this first positive traveling wave, as we have already calculated, has a magnitude of 20/3 volts. Then, since the reflection coefficient at the load is 1/3, here's the load at Z equals L, and so the reflection coefficient there is 1/3. So we take this 20/3 and multiply it by 1/3, and we get 29 volts headed back to the generator. It gets to the generator here, and then the generator reflection coefficient is minus 1/3. So we have minus 1/3 times 29ths, and that would give us minus 20 over 27 volts traveling back this way. And then when that reflects off the load, again there, the reflection coefficient is 1/3. So we take 1/3 times minus 20 over 27, and we get minus 20 over 81 volts going back in that direction. And if we went one more step, since the generator reflection coefficient is minus 1/3, we'd have minus 1/3 times minus 20 over 81, or a positive 20 over 243 if we went for the next reflection. But again, we're not required to do that. And then the only remaining part of this problem is to find the voltage at Z equals L over 2. So that's here at Z equals L over 2 at T equals 3L over VP. So all you need to do is start at Z equals L over 2, that's the desired location, and then start going up until you reach the desired time. Now 3L over VP is right here. So we go up and we just keep count of all of the lines that we cross as we're going up to the desired time. And here we cross this one, so that's 20/3 volts. Then we cross this second one, and that's 29 volts. And we also cross this third one, which is minus 20 over 27 volts. But we don't cross any more lines in going from here up to 3L over VP. So we just take 20/3 volts plus 29 volts minus 20 over 27 volts, and that is 8.148 volts. And that would be the voltage at Z equals L over 2 at time 3L over VP. And that's it. That's all there is to this problem. So nice and simple problem, and one that I think, this is a good kind of problem to look for on a test. So that's it.